Imagine staring at the oldest light in the universe, a ghostly glow that's traveled across space for over 13 billion years to reach your eyes. This is the cosmic microwave background, the fading echo of the Big Bang itself, a snapshot of the universe when it was just a newborn, barely 380,000 years old. But this isn't just ancient light, it's a cosmic detective story, hiding clues about how galaxies formed, why the universe looks the way it does, and even what might happen to it in the distant future. And yet, the more we study it, the more mysteries we uncover, strange anomalies, puzzling patterns, and questions that defy our best theories. What if I told you this faint radiation holds secrets that could rewrite our understanding of reality? Tiny temperature fluctuations, barely a whisper above absolute zero, might reveal hidden dimensions or parallel universes. Vast, unexplained structures stretch across the sky, so enormous they challenge the very laws of physics. And then there's the cold spot, a bizarre, cosmic void so strange some scientists wonder if it's a bruise from a collision with another universe. These aren't just curiosities, they're cracks in the foundation of our knowledge, hints that there's something fundamental we're still missing about how everything began. Today, we're diving into 30 of the most mind-bending mysteries hidden within the cosmic microwave background. From the enigma of dark energy's grip on the universe to the unsettling way space itself might be shaped like a hall of mirrors, each discovery pulls us deeper into the unknown. This isn't just about science, it's about stepping to the edge of what we know and peering into the abyss. So buckle up, by the end of this journey you'll see the night sky differently. Not just as stars and emptiness, but as a vast, whispering archive of the universe's greatest secrets waiting to be decoded. One of the strangest puzzles lurking in the cosmic microwave background is something scientists call the axis of evil. At first glance, it sounds like the title of a sci-fi thriller, but this is very real, and it's throwing our understanding of the universe into question. When we map the tiny temperature variations in the CMB, we'd expect them to be scattered randomly like splatters of paint on a canvas. That's what the cosmological principle tells us. The universe should look roughly the same in every direction, with no preferred axis, no cosmic up or down. But that's not what we're seeing. Instead, these fluctuations seem to line up along a specific plane, almost as if the universe has a hidden equator, a direction that somehow matters more than others. This isn't just a minor oddity. If confirmed, it suggests something foundational in our models might be wrong. Some researchers argue it could be an artifact of measurement errors, a quirk in how we're interpreting the data. But even after multiple missions from WMAP to Planck, the signal stubbornly persists. Others propose wilder explanations. Could the fabric of space itself be twisted into an exotic shape, like a hall of mirrors on a cosmic scale? Or is this an echo of something even stranger, a remnant of conditions before the Big Bang, a fingerprint of an earlier epoch we can't yet comprehend? Then there's the unsettling possibility that this alignment hints at something beyond our universe. Some theories suggest our cosmos might have collided with another bubble universe in the distant past, warping space-time in ways we're only beginning to detect. Imagine dropping a rock into a still pond. The ripples would spread outward in a pattern, not random splashes. Could the axis of evil be the wake of such a collision? Whatever the answer, one thing is clear: this mystery isn't just about the CMB. It's a challenge to the very foundations of cosmology, a clue that the universe might be far stranger and far less uniform than we ever imagined. Now, let's turn our attention to a chilling enigma buried within the cosmic microwave background, literally. Nestled among the delicate temperature fluctuations is a region so cold it defies easy explanation. Scientists call it the cold spot, a sprawling anomaly roughly 70 times larger than our full moon on the sky. At first glance, you might think, so what? The CMB isn't perfectly uniform, we already knew that. But this isn't just a minor fluctuation. the cold spot is colder than our best models predict, as if someone carved a cosmic freezer into the fabric of the early universe. One leading theory suggests this could be the shadow of a supervoid, an immense, nearly empty region of space where galaxies are strangely scarce. If light from the CMB passed through such a void on its way to us, it would lose energy, appearing colder in that patch. The problem, even the largest known voids can't fully account for the cold spot's extreme temperature drop. It's like trying to explain a glacier with a handful of ice cubes. Then there's the far wilder possibility. What if this is a cosmic bruise, a relic of a collision with another universe? In the multiverse scenario, our universe might be one bubble among countless others. If two bubbles grazed each other long ago, the energy of that impact could have left a marker, a cold, distorted region in the CMB. It's a tantalizing idea, but here's the catch. No current model cleanly predicts what such a collision should look like. Without a definitive signature, the multiverse explanation remains more poetry than proof. And then there's the simplest answer, the one scientists dread most. What if the cold spot is just a statistical fluke? After all, when you map the entire sky, some anomalies are bound to appear purely by chance. But calculations show the odds of something this extreme happening randomly are less than 2%. That's not impossible, but in science, we prefer answers that don't rely on cosmic coincidence. So where does that leave us? The cold spot stubbornly resists every explanation we throw at it. It's too cold for a void, too vast for a fluke, and too enigmatic for even the multiverse to claim without controversy. This isn't just a puzzle, it's a mirror held up to the limits of our understanding. Every time we think we've got a handle on the universe's blueprint, the cold spot whispers, "Think again." If you hold your hands at arm's length, they span about 10 degrees of the night sky, a tiny patch in the grand cosmic canvas. Now picture this, the cosmic microwave background should, in theory, show subtle connections between regions even 60 degrees apart or larger, like invisible threads stitching the universe together. These correlations are a smoking gun of inflation, the explosive expansion thought to have ironed out the early universe's wrinkles. But here's the twist: when we search for these large-scale patterns, they're missing. It's as if the universe forgot to follow its own blueprint. This isn't just a minor discrepancy. Inflation predicts that quantum fluctuations from the universe's first moments should have left imprints across vast distances, creating a statistical kinship between far-flung parts of the sky. Yet when scientists analyze the CMB's temperature variations, those expected correlations vanish at scales wider than 60 degrees. It's like listening to a symphony and realizing the violins and cellos are playing in perfect sync, but the entire brass section is mysteriously silent. Some researchers argue this could mean inflation wasn't as uniform as we thought. Maybe the early universe expanded in fits and starts, leaving gaps in the cosmic fingerprint. Others propose even more radical ideas. Perhaps the universe isn't as vast as we believe, and what we're seeing is the edge of its true scale, like a fish realizing its pond has walls. Then there's the unsettling possibility that our statistical tools are simply inadequate, that the correlations are there but hidden in noise we don't yet know how to filter. But the most tantalizing explanation, this could be evidence of pre-Big Bang physics, relics of an era when the laws of nature operated entirely differently. Imagine finding a fossil that predates the very concept of time, a relic so ancient it reshapes our origin story. That's the scale of what might be lurking in this absence. The missing correlations aren't just blank spaces, they're silent screams from the dawn of everything, hinting that our universe's first chapter is far stranger than we've dared to imagine. Buried in the faint whispers of the cosmic microwave background lies another spine-tingling anomaly, one that makes the universe seem oddly coordinated. When scientists decompose the CMB's temperature patterns into mathematical components called multipoles, The lowest order ones, the quadrupole and octopole, should point in random directions like dice tossed onto a table. Instead, they're eerily aligned, as if the universe rolled snake eyes against all odds. This isn't just a quirk, it's a direct challenge to one of cosmology's bedrock principles, that the universe is isotropic, meaning it should look the same in every direction. So why does this alignment rattle physicists? Think of the CMB as a symphony, where each multipole represents a different instrument. The quadrupole and octopole are like the bass and cello sections. They set the foundational tone. In a truly random universe, these sections should play independently, yet somehow their music syncs up along a shared axis, almost as if hidden sheet music is guiding them. Some researchers have combed through the data, checking for instrument errors or galactic dust obscuring the signal, but the alignment persists across multiple missions. It's too precise to dismiss as noise. This opens the door to radical possibilities. Could gravity itself behave differently on cosmic scales, warping space-time in ways we don't yet understand? Modified gravity theories, like MUND, suggest our equations might be incomplete, that dark matter's fingerprints could actually be the tug of unaccounted-for physics. Others propose an even wilder idea, that these alignments trace back to the universe's birth, hinting at a primordial magnetic field or a space-time structure twisted like a kaleidoscope. But the most unsettling implication: if the universe has a preferred direction, it means we might occupy a special place within it, a direct affront to Copernicus's principle that Earth, and by extension humanity, isn't cosmically central. Yet here we are, staring at data that whispers, maybe the universe isn't as indifferent as we thought. Whether this alignment is a clue to deeper laws or a cosmic illusion, one thing's certain: it's proof that the CMB still holds puzzles capable of appending everything we think we know. Picture a perfectly round balloon inflating, except one side stretches faster than the other, leaving it lopsided. That's essentially the puzzle we face with the cosmic microwave background's hemispherical power asymmetry. When we map the CMB's temperature variations across the sky, one half consistently shows stronger fluctuations than the other, as if the universe's infancy had a loud side and a quiet side. This isn't just a minor imbalance, it's a glaring crack in our assumption that the Big Bang's aftermath was uniform. One leading explanation points to inflation, the universe's exponential expansion in its first moments. Could inflation have been uneven, like a cosmic gust of wind hitting one side harder than the other? If so, that initial push might have left one hemisphere with more pronounced wrinkles in spacetime. But here's the problem: standard inflation models treat the universe like a well-mixed batter, predicting symmetry everywhere. To explain the asymmetry, we'd need to rewrite the recipe, adding ingredients like exotic energy fields or uneven quantum fluctuations. Then there's the ghostlier possibility: gravitational waves from a previous universe. Some theories suggest our cosmos might be one in a chain, with a prior universe collapsing and rebounding into ours. The death throes of that ancient cosmos could have sent shockwaves through spacetime, imprinting our CMB with a telltale lopsidedness. It's a poetic idea, like finding seashells on a mountain, evidence of a long-vanished ocean. But skeptics argue the asymmetry might not be cosmic at all. Could it stem from something mundane, like dust in our own galaxy, subtly filtering the CMB's light? Or worse, what if it's just a statistical mirage? After all, even a fair coin can land heads up 10 times in a row by chance. Yet multiple missions from Planck to WMAP keep confirming the signal. The odds of this being random are slim, leaving us with a universe that seems stubbornly unbalanced. This mystery forces us to confront an uncomfortable truth: the cosmos might not play by the neat, symmetrical rules we've written for it. Whether the asymmetry reveals a flaw in inflation, echoes of a pre-Big Bang universe, or something entirely unforeseen, it's a reminder that the CMB isn't just a relic, it's a mirror, reflecting how much we still don't understand about the universe's first breath. The cosmic microwave background isn't just a static snapshot. It's subtly warped by Earth's motion through space, creating a pattern scientists call the dipole. Imagine walking through a snowstorm. The flakes appear to come at you faster from the front, creating a hotter direction in the CMB, while the opposite side looks slightly cooler. This effect should perfectly match our measured velocity relative to the CMB's rest frame. But here's the catch: when we compare this dipole to the motion inferred from galaxy surveys, the collective tug of all nearby cosmic structures, the numbers don't line up. It's as if the universe is playing a shell game, hiding part of the force driving our motion. This discrepancy isn't just a rounding error. The CMB dipole suggests we're moving at roughly 600 kilometers per second, but galaxy surveys account for only about half that speed. So what's pulling us, or rather, everything in our galactic neighborhood toward some invisible attractor? One tantalizing answer is dark flow, a mysterious large-scale drift of galaxy clusters that seems to point toward something massive beyond the observable universe. Picture a river current dragging leaves along. If we're caught in a cosmic current, it could mean there's a structure so enormous, a supercluster or even a gravitational anomaly from another universe, that its gravity reaches across billions of light years. Then there's the unsettling possibility that our local universe is far lumpier than we've mapped. Vast concentrations of dark matter, undetected because they don't emit light, could be yanking us off course. Think of it like hiking through a forest at night, convinced you're walking straight only to realize hidden slopes have been steering you all along. Some models suggest these dark matter hills could stretch hundreds of millions of light years, their gravity subtly warping the motions of entire galaxy superclusters. But skeptics argue the mismatch might not be cosmic at all. Could it stem from errors in how we measure galaxy motions or interpret the CMB's distortions? For instance, if our Milky Way's halo of hot gas is uneven, it might scatter the CMB's light in ways we haven't fully accounted for. Or perhaps the dipole itself isn't purely kinematic. What if part of it's primordial, a relic fluctuation from the Big Bang that masquerades as motion? The implications ripple far beyond a missing number. If dark flow is real, it hints at structures so vast they defy the cosmological principle, the idea that the universe should look roughly uniform on large scales. And if unseen matter is the culprit, it means our census of the cosmos is even more incomplete than we feared. Either way, the missing dipole isn't just a puzzle, it's a breadcrumb trail leading to one of two terrifying possibilities: that we're not alone in the multiverse, or that we're profoundly blind to the architecture of our own. The cosmic microwave background's near-perfect uniformity is one of its most baffling features, a smoothness so precise it shouldn't be possible. Picture two friends standing at opposite ends of a stadium, each holding a cup of coffee. By some miracle, those coffees are identical in temperature, down to a millionth of a degree. Now imagine that stadium is the observable universe, and those friends are regions of space separated by 90 billion light years. According to the laws of physics, those regions could never have exchanged heat or information. The speed of light hasn't allowed enough time for them to interact since the Big Bang. Yet the CMB's temperature is uniform across these vast distances, as if the cosmos coordinated its conditions faster than light itself. This is the horizon problem, a paradox that keeps cosmologists awake at night. How could patches of the universe with no causal connection, regions that were never close enough to influence each other, end up so perfectly synchronized? The leading solution is cosmic inflation, a theory proposing that the universe underwent a brief, exponential expansion in its first fraction of a second. Think of it like stretching a crumpled sheet of fabric until every wrinkle vanishes. Inflation would have ironed out irregularities, leaving behind the smoothness we see in the CMB. But while inflation explains the what, it still leaves gaps in the how. For starters, inflation requires a mysterious energy field, the inflaton, to drive this hyper-expansion. We've never detected this field directly, and its properties remain purely theoretical. Worse, inflation's fine-tuning problem looms large. The expansion had to start and stop with absurd precision. Too fast and space-time would have ripped itself apart. Too slow, and the universe would have collapsed back in on itself. It's like balancing a pencil on its tip for an eternity, only to have it fall exactly when needed. Then there's the multiverse complication. Many inflation models predict an endless cascade of universes, each with different physical laws. If true, our universe's uniformity might just be a fluke, a lucky roll of the dice in an infinite cosmic casino. But without observable evidence, this remains speculative, more philosophy than physics, and perhaps the most unsettling gap of all. Inflation doesn't entirely erase the horizon problem. It pushes it further back in time, replacing one mystery with another. Instead of asking how distant regions thermalized, we now ask how inflation itself began uniformly. It's like tracing a river's source only to find another, even deeper spring. The CMB's uniformity is both a triumph and a taunt. It confirms inflation's broad strokes while exposing the frayed edges in our understanding. Every answer leads to sharper questions, a proof that even the smoothest cosmic canvas hides turbulence beneath its surface. Deep within the faint glow of the cosmic microwave background lies a ghostly fingerprint, one that shouldn't exist. Scientists call it primordial magnetism, the whisper of magnetic fields threading through the universe when it was just a newborn. These fields are puzzling not just because they're there, but because nothing in our standard models predicts them. Magnetic fields require moving electric charges like those in stars or galaxies. But the early universe was too young for stars, too smooth for the chaos needed to generate such forces. So how did magnetism emerge before the cosmos had the ingredients to create it? The clues hide in the CMB's polarization, the subtle alignment of light waves as they scatter off particles in the early universe. Certain swirls in this polarized light, known as B modes, could be the scars of primordial fields twisted by the fabric of spacetime itself. It's like finding fossilized footprints in a place no creature should have walked. Some researchers argue these fields were born during cosmic inflation, when quantum fluctuations stretched to cosmic scales, potentially leaving behind magnetic imprints. Others propose they erupted from phase transitions in the early universe, moments when the very laws of physics changed abruptly, like water freezing into ice across the cosmos. But here's where things get contentious. Not all B modes come from primordial fields. Dust in our own galaxy can mimic the signal, and gravitational waves from inflation, another holy grail of cosmology, create similar swirls. Teasing apart these possibilities is like listening for a single instrument in a symphony where half the orchestra is playing the same note. The Planck satellite's data hinted at primordial magnetism, but the signal hovered just below the threshold of certainty, a cosmic maybe. Then there's the staggering implication. If these fields are real, they've shaped the universe in ways we're only beginning to grasp. They could have guided the formation of the first galaxies, acting as invisible scaffolding for cosmic structure. Some theories even suggest they're tied to dark matter or hidden dimensions, a thread woven into the universe's deepest laws. But without definitive proof, primordial magnetism remains a tantalizing shadow, a mystery that forces us to ask, what else don't we know about the universe's first moments? This isn't just about filling in a gap in our models. It's about confronting the possibility that the early universe operated by rules we haven't yet written, rules that might still govern the cosmos today, hidden in plain sight. The universe isn't just expanding, it's being pulled. That's the startling conclusion behind the phenomenon known as dark flow, a mysterious drift of galaxy clusters that seems to defy the predictable spread of cosmic expansion. When astronomers mapped the motion of hundreds of clusters using the cosmic microwave background as a reference frame, they found something unsettling. These colossal structures aren't moving randomly. Instead, they're streaming in the same direction at breakneck speeds, as if tugged by some unseen force. And not just any force, something so massive its gravity reaches beyond the edge of the observable universe. What could possibly exert such influence? One possibility is a supermassive structure lurking in the cosmic shadows, a concentration of matter so vast it warps the fabric of space-time across billions of light years. Picture standing on a beach, feeling the tide tug at your feet, even though the ocean stretches far beyond the horizon. That's dark flow, the cosmic equivalent of sensing an ocean we can't see. Some theories suggest it could be a remnant of pre-inflationary physics, a scar from the universe's birth when regions outside our observable bubble left their mark. Others propose an even wilder idea, that we're feeling the gravitational echo of a neighboring universe, a parallel cosmos brushing against our own in the multiverse's infinite tapestry. But skeptics aren't convinced. Could this coordinated motion be an illusion, a trick of incomplete data or measurement biases? After all, mapping galaxy clusters across such distances is like trying to track a flock of birds through fog. What looks like a unified flight path might just be gaps in our vision. The Planck satellite's later analyses muddied the waters further, finding weaker evidence for dark flow than earlier studies, yet the signal hasn't vanished entirely. It lingers at the edge of statistical significance, like a whisper just loud enough to keep scientists listening. The implications are profound. If dark flow is real, it shatters a cornerstone of modern cosmology, the cosmological principle which assumes the universe is homogeneous on large scales. Instead, we'd be forced to confront a cosmos with a hidden architecture, one where our observable universe is just a room in a far grander and stranger mansion. Even if it's an artifact of errors, the debate reveals how much we still don't understand about the CMB's subtleties. Dark flow isn't just a mystery about motion. It's a question about the limits of our cosmic horizon and whether something unimaginable lies just beyond it. The Big Bang didn't just create space and time, it was the ultimate cosmic alchemist, forging the universe's first elements in a fiery fusion reactor. According to our best models, this process, called Big Bang nucleosynthesis, should have left behind a specific recipe of hydrogen, helium, and trace amounts of lithium. And for the most part, the predictions match reality except for one glaring exception. When astronomers measure lithium levels in the oldest stars, celestial time capsules from the early universe, they find only about a third of what the CMB's data says should be there. This isn't just a minor accounting error, it's a cosmic discrepancy that threatens to unravel our understanding of nuclear physics itself. So where did the lithium go? One possibility is that our models of nucleosynthesis are incomplete. The calculations rely on precise nuclear reaction, rates the probabilities that atomic nuclei will collide and fuse in the early universe's extreme conditions. If even one of these rates is slightly off, it could throw off the entire lithium prediction. Some theorists suggest revising the cross-section of a key reaction involving beryllium, which decays into lithium. Others propose that unknown nuclear resonances, short-lived quantum states, might have altered the primordial element production like a hidden switch in the cosmic factory. But there's a wilder solution lurking in the shadows. What if the missing lithium was destroyed by something we can't see? Actions, hypothetical particles born from quantum field theory, could have decayed in the early universe, releasing energy that scrambled lithium nuclei. Or maybe primordial black holes, tiny, dense remnants from the Big Bang, swallowed lithium atoms whole, leaving fewer behind for us to observe. These ideas sound like science fiction, but they're grounded in serious physics, and they hint at gaps in our knowledge that go far beyond a single element's abundance. Then there's the unsettling third option. What if the ancient stars themselves are hiding the truth? These stellar relics are thought to preserve the pristine chemistry of the early cosmos, but what if their interiors have been slowly burning lithium over billions of years? Some models suggest turbulent mixing could have dragged lithium deeper into these stars where nuclear reactions destroyed it. But if that's the case, why don't we see similar depletion in other elements? The lithium problem refuses to yield an easy answer. What makes this mystery so profound isn't just the missing atoms, it's what they represent. Lithium is a litmus test for the entire Big Bang framework. If our predictions are wrong here, what else might we have miscalculated? The CMB gives us an exquisitely precise snapshot of the early universe, but the lithium deficit whispers that somewhere in the fine print of cosmic history, there's a line we've misread. Whether the solution lies in tweaked nuclear rates, exotic particles, or stellar sleight of hand, one thing is clear: this isn't just about lithium. It's about whether we've truly decoded the universe's first moments, or if we're still missing a fundamental piece of the story. Imagine two clocks, each built by master craftsmen using the most precise tools available. One is calibrated to the distant echoes of the cosmic microwave background, the other to the flicker of nearby stars. Both should tick in perfect sync, both measure the same universe after all. Yet as scientists compare these cosmic timekeepers, they're finding a glaring mismatch, one that's grown too large to ignore. This is the Hubble tension, a crisis in cosmology that pits our understanding of the early universe against the reality we see around us today. On one side, we have the CMB's version of the Hubble constant, the rate at which the universe is expanding calculated by painstakingly analyzing the subtle patterns in the ancient light. This method gives us a value of around 67 kilometers per second per megaparsec. But when astronomers measure the expansion using nearby supernova and pulsating stars, the number jumps to roughly 73. That 6-kilometer gap might sound trivial, but in the precise world of cosmology, it's a chasm. It's like two GPS systems giving you directions to the same location. One puts it a mile west of the other. At some point, you have to admit, something's fundamentally wrong with the map. So what's breaking our cosmic ruler? One camp argues for new physics, suggesting dark energy. The mysterious force accelerating the universe's expansion might not be constant after all. What if it's growing stronger over time or interacting with dark matter in ways we haven't accounted for? This would mean Einstein's cosmological constant, a cornerstone of modern physics, isn't so constant after all. Others propose even wilder fixes, like hidden dimensions subtly warping space-time or a fifth force of nature tugging at the cosmos. Then there's the sobering possibility that we're being fooled by our own measurements. Could local supernova be dimmer than we think, skewing distance calculations? Or is our galactic neighborhood unusually sparse, creating a pocket where expansion appears faster? Some researchers even suggest the Milky Way sits in a cosmic void, a vast, bubble-like region of lower density, throwing off our local readings. But here's the rub: the more we refine our tools, the starker the discrepancy becomes. The latest CMB data from the Atacama Cosmology Telescope and local supernova surveys have only deepened the divide, each doubling down on their conflicting numbers. The Hubble tension isn't just academic quibbling. If it points to new physics, we might be on the verge of overturning a century of cosmological dogma. If it's observational error, it reveals how fragile our grasp of the universe remains, even with cutting-edge technology. Either way, this clash between the ancient and modern cosmos is a humbling reminder: the universe doesn't owe us consistency. And sometimes, the most revealing truths come from the places where our best models break down. Dark energy is supposed to be the universe's ultimate straight arrow, consistent, unchanging, the silent force behind the accelerating expansion of space. The Standard Model pins it to a cosmological constant, an energy density so uniform that its equation of state, represented by the letter W, is locked at exactly -1. But what if the cosmic microwave background is telling us we've oversimplified the cosmos's greatest mystery? Recent analyses of the CMB's subtle distortions suggest W might not be -1 after all. It could fluctuate, evolve, or even dip into territory so bizarre physicists call it phantom energy, a hypothetical dark energy with W less than -1. This isn't just a tweak to the formula, it's a seismic shift that could rewrite the universe's expiration date. If dark energy's equation of state deviates from -1, it implies this force isn't static. Imagine a car's cruise control slowly pressing harder on the gas pedal over time. Phantom energy would be the cosmic equivalent, driving the universe's expansion faster and faster until the very fabric of space-time can't keep up. The consequences are apocalyptic. In one scenario, the universe could face a big rip, where phantom energy grows so dominant it tears apart galaxies, then solar systems, and eventually atoms themselves. It's not just the end of stars, it's the unraveling of reality's building blocks. But how does the CMB hint at this possibility? The key lies in how dark energy influences the universe's large-scale structure. If W varies, it would leave subtle fingerprints in the CMB's temperature and polarization patterns, altering how quickly galaxy clusters formed in the universe's adolescence. Some studies claim to spot these anomalies, hints that dark energy's grip tightened or loosened over cosmic time. The trouble is, these signals flirt with the edge of statistical significance, like whispers drowned out by cosmic static. Even Planck's precision data hasn't settled the debate, leaving room for both skeptics and believers to dig in. Then there's the unsettling alternative. What if the phantom energy signal isn't dark energy at all, but something far stranger? Modified gravity theories, like Galilean models, can mimic dark energy's effects without invoking exotic fields. Or perhaps we're seeing the echo of a primordial phase transition, a moment when the vacuum of space itself changed states, releasing latent energy like steam condensing into water. The CMB might be holding clues to these possibilities, but teasing them apart requires peeling back layers of cosmic noise with near impossible precision. The stakes couldn't be higher. If dark energy is truly phantom, the universe's fate shifts from a slow fade into cold darkness to a violent cosmic crescendo. And if it's something else entirely, that would mean we've misunderstood one of the universe's most fundamental forces, a humbling reminder that even our best theories are provisional, penned in erasable ink on the pages of cosmic history. The CMB's whispers about W aren't just academic curiosities, they're a countdown clock ticking toward whichever strange destiny the universe has chosen for itself. Neutrinos are the cosmic ghosts of the particle world, so light and elusive they barely interact with matter at all. Yet these phantom particles might hold the key to one of the biggest mismatches in modern physics. When cosmologists use the cosmic microwave background to weigh neutrinos, they get numbers that clash with results from particle physics experiments. The CMB suggests neutrinos are feather light, their masses adding up to less than 0.1 electron volts. But underground detectors like Catron, designed to catch neutrinos in the act of radioactive decay, hint they could be 5 times heavier. It's as if the universe gave us 2 different instruction manuals for the same particle and neither quite fits. So why does the CMB care about neutrino mass in the first place? Picture the early universe as a pot of boiling water, with neutrinos zipping around like steam particles. The heavier they are, the more they tug on space-time, altering how matter clumps together during cosmic dawn. These imprints linger in the CMB's temperature fluctuations, letting us weigh neutrinos by their gravitational shadow. But here's the catch: that shadow depends on more than just mass. If neutrinos have secret interactions, ways to swap flavors or decay invisibly, the CMB scale could tip unexpectedly. That's where sterile neutrinos enter the scene. These hypothetical cousins of ordinary neutrinos don't even feel the weak force, making them nearly impossible to detect directly. Yet if they exist, they'd skew the cosmic neutrino census, tricking the CMB into underestimating true masses. Think of it like trying to count apples in a dark room. You might miss the ones hidden in the back, throwing off your total. Some models suggest sterile neutrinos could also explain anomalies in reactor experiments, where detectors see fewer neutrinos than predicted. But skeptics argue the discrepancy might stem from something simpler: flaws in how we interpret the data. Galaxy surveys, which map the universe's large-scale structure, sometimes align better with particle physics-heavier neutrinos. Could the CMB be missing a piece of the puzzle, like hidden biases in how we model cosmic inflation? Others propose wilder fixes. Maybe neutrinos interact with dark matter through an unknown force, or their masses change over cosmic time. The stakes are higher than they seem. If neutrinos are heavier than the CMB suggests, it would mean the universe contains more mass than we've accounted for, mass that could bend the fate of the entire cosmos. And if sterile neutrinos are real, they'd be the first particles outside the standard model, cracking open a door to uncharted physics. This isn't just about weighing ghostly particles. It's about whether we've been reading the universe's scales wrong all along, and what else might be hiding in the margins. Somewhere in the murky depths of cosmic history, the universe experienced a second Big Bang, not of matter, but of light. Known as reionization, this epoch saw the first starlight tear apart the fog of neutral hydrogen that had cloaked the cosmos since the Big Bang. The cosmic microwave background holds scars from this violent transition, imprinted in its polarization patterns like a fossilized lightning bolt. But here's where the story gets tangled. When we compare the CMB's reionization timeline to the one written in the stars themselves, the distant galaxies we observe with telescopes like Hubble and James Webb, the dates don't match. It's as if the universe's biography has two conflicting first chapters. The CMB tells us reionization was a slow burn, beginning around redshift 15 and stretching over hundreds of millions of years. But galaxy surveys paint a different picture, one where early stars and quasars lit up the cosmos much later, around redshift 6. That leaves a glaring gap. If the first galaxies weren't bright enough or numerous enough to ionize the universe when the CMB says it happened, what did? One radical answer lurks in the shadows: supermassive black holes born not from dying stars, but from the direct collapse of primordial gas clouds. These direct collapse black holes could have formed in the universe's first 100 million years, pumping out vast amounts of ionizing radiation long before ordinary stars took center stage. Imagine a forest fire ignited not by campers, but by lightning from a storm no one saw coming. Then there's the dark horse candidate, literally. Could dark matter, the universe's most elusive ingredient, have played a role? Some theories suggest certain types of dark matter particles might decay or collide, releasing bursts of energy capable of stripping electrons from hydrogen atoms. It's a long shot, but if true, it would mean reionization wasn't just the work of stars and galaxies. It was a cosmic team effort, with dark matter pulling invisible strings. But perhaps the simplest explanation is the most humbling: we're reading the signals wrong. The CMB's polarization data is famously delicate, like trying to reconstruct a symphony from a recording full of static. Subtle biases in how we model interstellar dust or foreground emissions could skew our reionization estimates. Meanwhile, high redshift galaxy searches are plagued by selection effects. Bright objects are easier to spot, potentially hiding a population of faint, early stars that did the heavy lifting. The reionization paradox isn't just about fixing a timeline. It's a confrontation with how little we know about the universe's awkward adolescence, those chaotic years between its birth in the Big Bang and the maturity we see today. Whether the solution points to black holes, dark matter, or observational blind spots, one thing is clear: the cosmos has a knack for revealing its secrets one contradiction at a time. The cosmic microwave background paints a picture of a universe that's geometrically perfect, flat as a sheet of paper, with space stretching endlessly in every direction. This isn't just an aesthetic preference, it's a prediction baked into inflation theory, which suggests the universe's explosive early expansion should have ironed out any curvature like a cosmic steamroller. But when other telescopes peer into the distant cosmos, they catch whispers of something off. Some galaxy surveys and gravitational lensing measurements hint at the faintest positive curvature, as if the universe is subtly closed like the surface of a balloon. The discrepancy is small, less than 1%, but in cosmology, even a whisper can upend everything. So why the tension? One possibility is that inflation didn't play out quite how we thought. Most models assume a smooth, relentless expansion, but what if it stuttered or wobbled, leaving behind tiny kinks in spacetime's fabric? Think of it like blowing up a balloon with uneven breath. Some patches might stretch tighter than others. Alternative inflation scenarios, like those involving multiple energy fields or phase transitions, could allow for just enough curvature to match the observational hints without abandoning flatness entirely. Then there's the elephant in the room: systematic errors. Measuring the universe's shape is like trying to gauge the Earth's curvature from a single hilltop. Galaxy surveys rely on complex calibrations to map distances, and even the slightest bias, like misjudging how dust dims starlight, could skew the results. The CMB, meanwhile, infers flatness indirectly from the apparent size of temperature fluctuations. If something in the early universe, like primordial magnetic fields or exotic dark matter interactions, altered how those fluctuations propagate, we might be misreading the cosmic blueprint. But the most tantalizing explanation lies in the shadows of our calculations. The standard model assumes dark energy behaves perfectly uniformly, like an invisible mist filling space. Yet if dark energy's strength varies over time or clumps unevenly, it could mimic the effects of curvature. Picture a funhouse mirror. What looks like a bent universe might just be the reflection of something stranger warping the glass. The curvature tension isn't just academic nitpicking. If the universe is slightly closed, it would mean our entire cosmic history, from inflation's endgame to the fate of spacetime, needs rewriting. A closed cosmos could eventually collapse in a big crunch, turning the universe's expansion story into a tragic loop. Or it might hint at a topology so bizarre, the universe folds back on itself like a Möbius strip, with distant galaxies eventually repeating like patterns in a kaleidoscope. For now, the data dances on a knife's edge. The CMB's precision is undeniable, but the whispers from other probes refuse to fade. Whether this tension reveals a flaw in our models, a hidden layer of physics, or just the limits of our measurements, one thing's certain: the universe's geometry isn't just a backdrop. It's a living question, and the answer might rewrite the rules of reality itself. The universe might have had a secret phase, one so brief we'd almost miss it if not for the faint fingerprints it left in the cosmic microwave background. This is the early dark energy hypothesis, a radical idea suggesting that before recombination, that pivotal moment when the first atoms formed, dark energy didn't just exist, it pulsed, surging in intensity before vanishing like a cosmic mirage. If true, it could explain some of the CMB's most nagging anomalies, particularly the way small-scale temperature fluctuations don't quite match our predictions. It's as if the universe's opening act had an unscripted twist, one we're only now beginning to decipher. Why propose such an exotic idea? The math behind the CMB's fluctuations hinges on precise details about how matter clumped together in the early universe. But when we compare theoretical models to actual observations, there's a mismatch at smaller scales, a slight oversmoothing that suggests something may have been tampering with gravity's grip during those critical first few 100,000 years. Early dark energy could be the culprit. Picture it like a temporary cosmic repulsor field, briefly counteracting gravity's pull and slowing the growth of structure just enough to leave a telltale mark in the CMB's patterns. The evidence is subtle but tantalizing. Measurements from the Atacama Cosmology Telescope and the South Pole Telescope have detected a curious suppression in the CMB's power spectrum at scales around 1 degree. This isn't just noise, it's a consistent signal that aligns eerily well with simulations where early dark energy was in play. Think of it like finding a fossil with an extra set of vestigial wings. Something's off in the evolutionary timeline, and this hypothesis offers a plausible explanation for the oddity. But here's where things get thorny. Early dark energy isn't the only candidate vying to explain these anomalies. Competing theories like interacting dark matter or modifications to Einstein's gravity can produce similar effects. To disentangle the possibilities, scientists are turning to the CMB's polarization data, hunting for unique swirls or distortions that could act as a smoking gun. Early dark energy would leave specific imprints in these patterns, like a signature scrawled in the margins of cosmic history. The implications stretch far beyond fixing a glitch in our models. If early dark energy was real, it means the universe's expansion hasn't been a steady march but a series of fits and starts, with dark energy flickering on and off like a faulty cosmic light switch. That raises even bigger questions. What triggered this phase? Could it happen again? And most unsettling of all, are we mistaking the universe's rhythm for a constant beat when it's really a stutter? For now, the hypothesis remains just that, a compelling but unproven idea. Yet it embodies the spirit of cosmology at its best, daring to rewrite the universe's story when the data whispers that we've missed a page. Whether early dark energy joins the pantheon of accepted physics or fades into obscurity, its very proposal is a reminder that the cosmos still holds surprises, and that even the faintest anomalies can lead to the most revolutionary revelations. When we look at the cosmic web, the vast, intricate network of galaxies and superclusters stretching across the universe, something doesn't add up. According to our best simulations, dark matter's gravitational pull should have sculpted enormous megastructures by now, dense knots where thousands of galaxies cluster together like glitter caught in a spider's web. But when astronomers analyze the cosmic microwave background's weak gravitational lensing, the subtle way its light bends as it passes through these cosmic neighborhoods, they find a puzzling shortage. The lensing signal is weaker than expected, as if the universe's most massive structures are somehow missing. This isn't just a case of miscounting galaxies. Weak lensing acts like an X-ray for the cosmos, revealing the hidden scaffolding of dark matter that underlies visible structures. If the lensing signal is faint, it means entire superclusters, the titans of the cosmic web, might be less dense than our models predict. One possible explanation: dark matter isn't behaving the way we thought. Most theories assume it's cold, moving sluggishly and clumping easily under gravity's pull. But if dark matter has even a tiny bit of intrinsic motion, what scientists call warmth, it could resist collapsing into the densest knots, leaving the universe's architecture more sparsely furnished. Then there's the gravity angle. Einstein's theory of general relativity has passed every test we've thrown at it, from black hole shadows to binary pulsars. But what if it stumbles on cosmic scales? Modified gravity theories, like MUND or its relativistic cousins, tweak the equations to explain galaxy rotations without invoking dark matter. Yet these models struggle to replicate the CMB's precise patterns unless they're hiding an even stranger feature, like a scale-dependent strength that only kicks in across supercluster distances. Think of it like adjusting a radio's antenna. Maybe gravity's signal weakens just enough over vast stretches of space to explain the missing lensing. But before we rewrite the laws of physics, let's consider the observational hurdles. Mapping weak lensing is like trying to measure a shadow's blur in a sandstorm. The CMB's light has traveled 13 billion years, passing through countless distortions along the way. Just in our own galaxy, the ripple of gravitational waves, even the quirks of how telescopes process data could all conspire to dilute the signal. The Planck satellites team ran exhaustive checks, but some skeptics argue that even a small bias in how we filter foreground noise might leave superclusters looking artificially sparse. The implications ripple outward. If superclusters are genuinely less massive, it could mean dark matter interacts with itself or other particles in ways we haven't seen, perhaps scattering like billiard balls instead of slipping past unnoticed. Or it might hint that the universe's expansion history isn't as uniform as we've assumed, with patches of space expanding faster and leaving less time for structures to grow. Either way, the missing superclusters aren't just a census error. They're a cosmic breadcrumb trail leading us toward questions we're only beginning to ask about gravity's grip, dark matter's nature, and whether the universe's grandest structures still hold surprises we haven't imagined. Buried in the faint swirls of the cosmic microwave background's polarized light lies a clue so profound it could confirm one of cosmology's boldest ideas: cosmic inflation. Scientists call these fingerprints B modes, a specific pattern of polarization that, if found, would be the smoking gun of gravitational waves rippling through the universe's first trillionth of a second. The catch: the signal is absurdly weak, drowned out by a cacophony of cosmic noise, with interstellar dust posing as the ultimate imposter. The quest for primordial B modes is like searching for a whisper in a hurricane. When inflation stretched spacetime faster than light, it should have generated gravitational waves, ripples in the fabric of reality itself. These waves would have twisted the CMB's photons as they scattered off electrons, leaving behind a telltale curling pattern in the polarization. But nature loves a good disguise. Our own galaxy's dust emits polarized light that mimics B modes almost perfectly, like an actor stepping into the lead role without an audition. Even the tiniest dust grains, aligned by galactic magnetic fields, can produce false signals strong enough to fool the most sensitive telescopes. The stakes of this hunt couldn't be higher. If primordial B modes are real, they'd confirm inflation's wildest predictions, revealing the energy scale at which the universe's exponential expansion occurred. It would be like finding the signature of the cosmic architect, but after years of searching, from the South Pole telescope to the BICEP experiments, the results have been eerily silent. The most infamous case came in 2014, when BICEP-2 announced a detection that turned out to be dust's cruel mimicry. Since then, the upper limits on B modes have only tightened, leaving inflation's gravitational wave prediction hanging by a thread. Yet the absence of a signal might be just as revealing. Some theorists argue that null results could mean inflation happened at lower energies than expected, leaving gravitational waves too faint to detect. Others see it as a sign that inflation wasn't a single dramatic event but a subtler process, like multiple ripples merging into a smoother wave. And then there's the radical fringe. Maybe inflation never happened at all, and the universe's smoothness came from some other yet unknown mechanism. The B-mode enigma forces us to confront the limits of our tools. Next-generation experiments like the Simons Observatory and Lightbird are designed to tease apart dust's deception with unprecedented precision. They'll map the sky at multiple frequencies, isolating the CMB's true signal from galactic interference like a chef separating egg whites from yolks. But even if they find nothing, the search itself rewrites the boundaries of cosmology. Whether primordial B modes are waiting to be uncovered or forever lost to cosmic static, their elusive nature reminds us that the universe's greatest secrets often hide in the quietest places. The cosmic microwave background should be a textbook example of randomness, a symphony of tiny temperature fluctuations following the elegant bell curve of Gaussian statistics. But what if the universe left deliberate fingerprints in the noise? That's the heart of the non-Gaussianity debate, a high-stakes hunt for subtle deviations in the CMB's patterns that could rewrite our understanding of the Big Bang's first moments. At its core, Gaussianity implies that temperature variations in the CMB are purely random, like static on an old television. inflation, the leading theory of the universe's exponential expansion, predicts this noise should be nearly flawless, a consequence of quantum fluctuations stretched to cosmic scales. But if we spot even the slightest skew, a subtle clustering of hot or cold spots that defies randomness, it could mean inflation wasn't the solo act we've assumed. Imagine shaking a box of puzzle pieces and finding they've mysteriously sorted themselves. Some hidden hand must have intervened. Enter multi-field inflation. Most models rely on a single energy field, the inflaton, to drive the universe's expansion. But if multiple fields were at play, their interactions could have left behind telltale distortions in the CMB's Gaussian purity. Think of it like dancers performing in sync until a second dancer joins, introducing new steps that subtly alter the rhythm. These deviations, called primordial non-Gaussianity, would appear as faint correlations between temperature fluctuations at different scales, a cosmic echo of fields colliding in the early universe's chaos. Then there's the cosmic defect scenario. Topological defects, knots or cracks in spacetime formed during phase transitions in the early universe, could also disrupt the CMB's randomness. Picture freezing a lake as the ice forms, cracks and bubbles emerge. Similarly, as the universe cooled, defects like cosmic strings or domain walls might have left scars in the CMB's temperature map, creating localized non-Gaussian imprints. The Planck satellite's painstaking measurements have placed the tightest constraints yet on these anomalies. Its data suggests non-Gaussianity, if it exists, is vanishingly small, consistent with zero at the precision we've achieved. But here's the catch: Planck's limits still leave room for exotic physics. Some models of multi-field inflation predict signals just below current detection thresholds, hiding like whispers beneath the cosmic static. Meanwhile, certain defect theories remain stubbornly viable, their predicted signatures too subtle for even Planck's sharp eye. The implications ripple far beyond academic curiosity. If non-Gaussianity were confirmed, it would mean inflation was messier and more complex than our tidy models suggest, perhaps involving interactions between multiple dimensions or exotic particles. Conversely, if future experiments like the Simons Observatory push the bounds further and still find nothing, it could force a reckoning for alternative theories of cosmic origins, from bouncing cosmologies to holographic universes. This isn't just about refining a statistical model. It's a window into whether the universe's birth was a solo performance or a chaotic ensemble, and whether the CMB's pristine randomness is truly perfect, or if it hides the faintest traces of a deeper, untold story. The silence so far isn't an ending, it's an invitation to listen more closely. The cosmic microwave background's dipole, the hot and cold spots created by Earth's motion through space, might be hiding more than just our velocity. Buried within this simple Doppler shift is a tantalizing asymmetry, one that could rewrite the rules of cosmic structure. When scientists subtract our local motion from the dipole, they're left with a lingering imbalance, a hint that the universe's large-scale power distribution isn't as even as we've assumed. Some patches of the sky show stronger temperature fluctuations than others, as if the cosmos itself has a stronger heartbeat in certain directions. What could cause such a fundamental lopsidedness? One radical possibility involves superhorizon perturbations, fluctuations so vast they stretch beyond our observable universe. Picture standing in a valley surrounded by distant mountains. You can't see past the peaks, but their presence warps the local weather patterns. Similarly, gravitational imprints from regions outside our cosmic horizon could be subtly tugging at the CMB's fabric, creating the dipole's residual asymmetry. These perturbations wouldn't violate cosmic inflation. They'd just mean some quantum fluctuations got stretched to scales even larger than our visible universe. Then there's the observational elephant in the room. Could our own galaxy's dusty halo or unseen local voids be filtering the CMB's light unevenly? Just as smudges on glasses distort vision, interstellar dust might selectively dim certain dipole directions, leaving phantom asymmetries in the data. The Planck satellite's multi-frequency maps help correct for this, but some researchers argue even its sophisticated dust models could be missing cold, dense filaments that skew the signal. The most unsettling interpretation, this asymmetry might be evidence that the universe's initial conditions weren't perfectly random. Inflation predicts quantum fluctuations should distribute energy uniformly, but if the dipole anomaly holds, it could mean the Big Bang's dice were subtly loaded, that some primordial process imprinted a preferred direction on spacetime itself. Whether the answer lies in superhorizon shadows, galactic interference, or a cosmic tilt we've yet to comprehend, one thing's clear: the dipole isn't just a speedometer. It's a compass pointing toward the universe's hidden fractures. What if the universe's darkest secret isn't an invisible particle, but an avalanche of ancient black holes lurking unseen since the dawn of time? The cosmic microwave background might hold clues to this radical idea. Subtle distortions in the CMB's spectral energy, tiny deviations from its near-perfect thermal curve, could be the echoes of primordial black holes, hypothetical monsters born not from dying stars but from the raw chaos of the Big Bang itself. These relics would be unlike anything we've detected before, some as light as asteroids, others as massive as suns, all drifting through the cosmos like ghosts in the machine of space. The case for these shadowy objects rests on two startling possibilities. First, they could solve the dark matter puzzle. While traditional WIMP and actions remain elusive, primordial black holes wouldn't need exotic physics. They'd simply be ordinary matter compressed into gravitational traps so dense they emit no light. Imagine dark matter not as a cloud of mysterious particles, but as a swarm of black holes so ancient they predate the first stars. The CMB offers indirect evidence. Certain frequency distortions align with models where black holes subtly heated the early universe's plasma as they passed through it, like stones rippling a pond surface. Then there's the gravitational wave connection. When LIGO detected mergers between improbably heavy black holes, astronomers were stunned. Where did these giants come from? Primordial black holes could be the answer. Born in the Big Bang's fury, they might have clustered in dense pockets over billions of years, eventually spiraling into collisions that sent shudders through spacetime. The CMB's polarization patterns might hide traces of these events, imprints of gravitational waves so ancient they've stretched into near silence across cosmic time. But proving their existence is like hunting for footsteps in a sandstorm. The spectral distortions they'd cause are achingly faint, buried under noise from interstellar dust and later astrophysical processes. Some researchers argue alternative explanations like early supernova or exotic particle decays could mimic the same signals. And there's a glaring hurdle. If primordial black holes are abundant enough to account for dark matter, why haven't we seen their gravitational lensing effects on starlight? Microlensing surveys have turned up far fewer candidates than needed to explain the universe's missing mass. Yet the most tantalizing version of this theory dodges even that critique. What if these black holes aren't uniformly distributed but clumped in dense, invisible halos around galaxies, or worse? What if they're not black holes at all, but something stranger? Hypothetical objects like gravastars, black hole mimics with exotic cores, or quantum bounce remnants could leave similar CMB fingerprints while evading traditional detection. The stakes are cosmic. If primordial black holes are real, they'd rewrite not just dark matter's identity, but the universe's entire early history. Their formation would require conditions so extreme they'd push the limits of quantum gravity, perhaps even offering glimpses of physics beyond Einstein's equations. Every anomalous CMB distortion, every unexplained gravitational wave, becomes a potential breadcrumb leading back to the Big Bang's most violent moments. Until we know for sure, these phantom black holes remain both a tantalizing solution and a reminder. Sometimes the darkest secrets hide in the oldest light. String theory has long been the universe's most ambitious mathematical symphony, a framework so elegant it promises to unite all forces of nature under one equation. But for all its beauty, it's been notoriously difficult to test. That's where the cosmic microwave background comes in. Hidden within its ancient glow might be the faintest echoes of string theory's predictions, from cosmic strings stretching across spacetime to the warping of extra dimensions we can't even see. The question isn't just whether these imprints exist, it's whether we're mistaking mathematical hope for measurable reality. Take cosmic strings, for example. These hypothetical fissures in spacetime are nothing like the black holes or stars we're used to. Picture them as cracks in a frozen lake, one-dimensional scars left over from the universe's phase transitions in its earliest moments. According to string theory, these strings would be nearly indestructible, thinner than an atom but with the mass of a mountain range, vibrating at near light speed. As they whip through the cosmos, they'd tug on spacetime itself, creating telltale kinks in the CMB's temperature map sharp, linear discontinuities where the background radiation suddenly jumps. It's like finding a razor's edge slice across an otherwise smooth canvas. The hunt for these signals has turned up tantalizing maybes. Certain anomalies in the CMB, like the famed CSL1 feature observed in early data, seem to align eerily well with cosmic string predictions. But follow-up studies revealed mundane explanations, like overlapping galaxies mimicking the effect. The Planck satellite's exhaustive search found no conclusive evidence, leaving strings in a quantum superposition of possibility, neither confirmed nor ruled out. Then there's the extra dimensions angle. String theory requires at least 6 additional spatial dimensions beyond the 3 we experience, all curled up into unimaginably tiny shapes. If these dimensions exist, they could subtly alter how gravity propagates on cosmic scales, imprinting unique patterns in the CMB's large-scale structure. Imagine blowing air through a flute. The notes it produces depend on the instrument's hidden geometry. Similarly, the CMB's fluctuations might carry harmonics shaped by the universe's unseen dimensions. Some researchers argue that certain statistical asymmetries in the CMB align with these predictions, though the signal is buried deep in noise. But here's the rub: string theory is so flexible it can retrofit almost any observation. Like a master locksmith, it has a key for every lock, which makes it frustratingly hard to falsify. The CMB's anomalies could point to cosmic strings, or they could be statistical flukes, foreground contamination, or signs of completely unrelated physics. Even the theory's proponents admit we're in a gray area where elegance and evidence haven't yet shaken hands. That's why the stakes are so high. If the CMB ever reveals unambiguous proof of strings or extra dimensions, it would be the crowning achievement of theoretical physics, a validation of decades of abstract work. But if it doesn't, we're left with a haunting possibility that the universe's deepest truths might be beautiful, but not in the way we imagined. For now, the CMB remains the ultimate litmus test, holding up a mirror to our boldest ideas and asking, is this science or just a stunning piece of mathematical art? The cosmic microwave background might be more than just a relic of our universe's birth. It could be a palimpsest, its faintest irregularities scribbled over by encounters with other realities. Imagine the early cosmos as a froth of bubble universes, each inflating from its own Big Bang, occasionally brushing against one another like soap suds in a sink. If such a collision occurred, the energy released would leave a scar, a circular bruise in the CMB's temperature map, a region either unusually hot or cold depending on whether the other universe added energy or siphoned it away. The cold spot we mentioned earlier, some theorists argue it's the most promising candidate for such a mark, a phantom ache from a primordial impact we can't yet prove. But here's the catch: proving a multiverse collision isn't like confirming a new particle or galaxy. The signal would be subtle, buried under cosmic noise, and horrifyingly easy to dismiss as a statistical fluke. Worse, alternative explanations like cosmic voids or exotic magnetic fields can mimic the same patterns. It's like finding a footprint on a beach and debating whether it's from a human, a bear, or just a trick of the waves. The Planck satellite's data teased hints of anomalous rings in the CMB, but the evidence was too weak to claim a detection. Even if we found a perfect candidate, skepticism would linger, because how do you test a hypothesis about something forever outside our observable universe? Critics argue this is less science and more metaphysics, a cosmic Rorschach test where theorists see what they want to see. Without a way to observe or interact with other universes directly, the multiverse remains, by definition, untouchable. But supporters counter that the CMB's anomalies are the data unexplained signals begging for an explanation, whether we're comfortable with the answer or not. If the cold spot or other irregularities do stem from a collision, they'd imply a cosmos far stranger than we've imagined, one where universes jostle in an unseen sea, their boundaries permeable, their histories entangled. The debate exposes a deeper tension in cosmology. At what point does a theory become untestable, not because we lack technology, but because the universe itself hides the evidence? Multiverse models dodge this by predicting statistical fingerprints. If we find enough anomalies clustered in ways inflation can't explain, the case strengthens. Future CMB experiments like CMB-S4 aim to map polarization with such precision that even the faintest collision scars couldn't hide. Until then, the multiverse remains a shadow on the cave wall, a shape we can't quite recognize but can't ignore either. Whether it's a glimpse beyond the edges of reality or just a trick of the light, one thing's certain: the CMB's quietest whispers might be shouting secrets from worlds we'll never see. What if the laws of physics aren't as constant as we think? The cosmic microwave background might be hiding evidence that the universe's most fundamental numbers, the so-called constants that govern everything from the strength of electromagnetism to the speed of light, weren't always set in stone. Imagine the fine structure constant, that delicate ratio dictating how atoms absorb light, quietly shifting in the universe's infancy like a dial being turned. This isn't science fiction. Subtle fingerprints in the CMB's spectral distortions and polarization patterns suggest these constants might have fluctuated during the cosmos's turbulent first moments, leaving echoes in the ancient light we observe today. The clues lie in how light interacted with matter during recombination when the first atoms formed. If the fine structure constant was slightly different back then, it would have altered the energy levels of hydrogen atoms, changing how they absorbed and emitted photons. The result: imperceptible shifts in the CMB's temperature and polarization, spectra ghostly anomalies that don't fit standard models. It's like finding a prehistoric cave painting where the hues don't match any known pigments, hinting at a lost chapter in the artist's technique. Some studies claim to detect these deviations, particularly in the CMB's large-scale fluctuations, though the evidence remains contentious, hovering at the edge of statistical significance. One radical theory that could explain such variations is variable speed of light cosmology. Proposed as an alternative to inflation, this idea suggests the speed of light wasn't always constant, but was drastically higher in the early universe, allowing distant regions to thermalize without requiring faster-than-light expansion. If true, it would mean the CMB's uniformity isn't a product of inflation's stretching but of light's fleeting agility in the cosmos's youth. Critics argue this introduces more problems than it solves, like why other constants tied to light's speed didn't also shift. But proponents point to the CMB's anomalous power spectrum as potential supporting evidence. Then there's the dark energy connection. If constants like the fine structure parameter did vary, they might have influenced dark energy's strength over time, offering a solution to the Hubble tension by tweaking the universe's expansion history. Picture a clock whose gears subtly change shape as it ticks, altering its tempo without breaking entirely. These ideas remain speculative, but they underscore a profound possibility. The the CMB isn't just a snapshot of the past. It's a time capsule holding relics of a universe whose rules were still being written. The implications ripple beyond cosmology. If constants can vary, even minutely, it challenges the very notion of physical laws as immutable truths. Are they more like cosmic habits, patterns that settled into place as the universe cooled? Future CMB experiments with unprecedented sensitivity to spectral distortions could turn this philosophical quandary into empirical fact, or consign it to the graveyard of beautiful but unproven ideas. Until then, the CMB's whispers keep us questioning. Are the constants truly constant, or are we just catching them in a fleeting moment of stability? The fabric of spacetime might not be as smooth as it appears. At scales trillions of times smaller than an atom, the universe could be seething with quantum foam, a turbulent sea of virtual particles and microscopic black holes bubbling in and out of existence. This frothy chaos is too tiny to see directly, but its fingerprints might be hiding in the cosmic microwave background, etched into the paths of photons that have traveled across the cosmos for over 13 billion years. Think of space as an ocean. From a distance, its surface looks glassy and still, but zoom in close enough and you'll find choppy waves and swirling eddies. Quantum foam suggests spacetime works the same way, perfectly smooth on large scales, but jagged and chaotic up close. As CMB photons traverse this subatomic turbulence, their journeys could be subtly distorted, like light shimmering through a heat haze. The question is, can we detect these nanoscale bumps in the universe's ancient afterglow? The hunt hinges on a phenomenon called photon dispersion. If spacetime is truly foamy, higher energy photons should traverse it slightly faster than lower energy ones, since their shorter wavelengths make them more sensitive to microscopic spacetime defects. Over billions of light years, that speed difference could accumulate, leaving a detectable smear in the CMB's spectral peaks. It's like rolling marbles of different sizes across a bumpy floor. The smallest ones would jostle more, arriving at slightly different times. But here's the cosmic twist. Gamma-ray bursts throw a wrench in the theory. These violent explosions produce photons across an enormous energy range, from radio waves to gamma rays. If quantum foam were disrupting photon speeds, we'd expect their highest energy light to arrive fractionally earlier than lower energy emissions. Yet when astronomers time these bursts with painstaking precision, they find no such lag, just a crisp, simultaneous arrival of all wavelengths. So does this rule out quantum foam? Not necessarily. Some theorists argue the foam's texture might be energy-dependent, smoother at higher energies, ironically making gamma rays less affected than expected. Others propose the foam operates on scales so minute that even the CMB's most energetic photons traverse it unaffected, like an ocean liner cruising over ripples too small to feel. The implications stretch beyond abstract physics. If quantum foam signatures exist in the CMB, they'd offer our first glimpse of quantum gravity, the holy grail of unifying Einstein's relativity with quantum mechanics. Imagine decoding the universe's smallest possible structures by studying its oldest light. Until then, the CMB's silence speaks volumes. Either spacetime's foam is finer than we can probe, or the universe's quantum foundations are stranger than we've dared to dream. Dark matter is supposed to be the universe's silent partner, invisible, stable, and utterly unchanging. But what if it's not? Tucked within the cosmic microwave background's faint hum are whispers of something far stranger. The possibility that dark matter particles, after eons of secrecy, might finally be revealing themselves by slowly unraveling. The idea hinges on a faint, unexplained emission line spotted in the CMB's spectral data, an excess of photons at a very specific energy. If confirmed, it could be the signature of dark matter decaying into lighter particles, a process that would release a delicate glow as it played out across cosmic history. This isn't just a minor anomaly. The signal, centered around an energy of 3.5 kilo electron volts, aligns eerily with predictions for sterile neutrinos, hypothetical dark matter candidates that could decay into ordinary neutrinos and X-ray photons. It's like hearing a distant radio station tuned to a frequency only dark matter should broadcast on. But here's the problem. When astronomers train X-ray telescopes on galaxy clusters where dark matter should be densest, most see nothing. The few detections that do exist, like the controversial line from the Perseus cluster, are hotly debated, with some teams claiming instrumental artifacts or plasma physics could mimic the signal. The stakes couldn't be higher. If dark matter decays, it upends decades of assumptions about its nature. Cold dark matter, the reigning theory, assumes these particles are inert like cosmic statues, unchanging since the Big Bang. But a decay signal would mean they're more like radioactive isotopes ticking away on cosmological timescales. That would demand entirely new physics. Perhaps dark matter interacts with itself through an unknown force, or maybe it's not a single particle at all, but a spectrum of species with varying lifespans. Then there's the timing problem. The CMB's integrated light spans billions of years, so any decay signal would represent a cumulative glow from across cosmic history. But local X-ray searches only probe dark matter's behavior today. If the decay rate slows over time, say, because it depends on the expanding universe's temperature, that could explain why we see hints in the CMB but not in nearby clusters. It's like comparing a long exposure photo to a snapshot. One captures faint, slow processes, the other misses entirely. Critics aren't convinced. They argue the CMB's spectral distortions are too subtle to claim a detection, buried under foreground noise from galactic dust and hot gas. Even Planck's precision data could only place upper limits on the signal, leaving room for doubt. And alternative explanations abound. Action like particles, cosmic strings, or even undiscovered atomic transitions in interstellar plasma could produce similar spectral bumps. Yet the tantalizing possibility lingers. Future CMB experiments like NASA PICO proposal aim to scour the sky for this decay signal with unprecedented sensitivity. If they find it, the implications would ripple far beyond dark matter's identity. It would mean the cosmos is filled with invisible fireworks, a slow-motion light show playing out in the darkness between galaxies, one that's been quietly shaping the universe's fate since the very beginning. Until then, this spectral whisper remains a cosmic Rorschach test, proof of dark matter's hidden life, or just another phantom in the noise. When photons from the cosmic microwave background finally broke free during recombination, they began their 13 billion-year journey across the universe untouched, undisturbed, or so we thought. But something strange happened along the way. Detailed observations reveal subtle irregularities in how these ancient photons scattered, as if an unseen hand gently nudged them off course. This isn't just random noise, it's a potential window into exotic physics operating at the universe's dawn, a moment when the rules we take for granted might have been rewritten. The smoking gun lies in the CMB's polarization patterns. As photons last interacted with electrons during recombination, most scattered in predictable ways, leaving behind clean, symmetrical imprints. But a fraction of these interactions show peculiar asymmetries, subtle twists that defy standard quantum electrodynamics. It's like watching a billiard game where most balls rebound predictably, except a few that inexplicably curve mid-flight. One explanation: unknown particles, lighter than electrons but just as capable of bumping photons off their paths, might have been present in the primordial plasma. These could be actions, hypothetical particles theorized to solve quantum puzzles, or even dark electrons from a parallel sector of physics operating alongside our own. Then there's the space-time angle. What if the fabric of the universe itself was subtly different during recombination? Modified gravity theories, like those that tweak Einstein's equations at cosmic scales, predict that photons propagating through the early universe's dense plasma would scatter differently than in today's sparse voids. Imagine light traveling through an ocean whose water inexplicably thickens or thins in patches. The ripples would carry traces of that inconsistency. Some models suggest this could arise from extra dimensions temporarily unfurling during the universe's hot early phase, leaving fingerprints in the CMB's scattering anomalies. But skeptics raise a sobering counterpoint. Our models of recombination aren't perfect. The process depended on precise atomic physics, hydrogen forming, photons decoupling, all while the universe expanded and cooled at breakneck speeds. If we've miscalculated even one variable, like the exact ionization fraction of the plasma or the cross-section of electron-photon interactions, it could mimic exotic scattering without requiring new physics. It's like blaming a magician for the impossible, only to realize the trick relied on a hidden mirror we hadn't noticed. The implications stretch beyond cosmology. If anomalous scattering holds up, it could mean recombination wasn't the clean, textbook process we've assumed. Instead, it might have been a battleground where known and unknown forces clashed, leaving behind scars in the CMB's light. Future missions like LIGHT-BIRD aim to dissect these polarization anomalies with razor precision. Until then, the universe's oldest photons remain both messengers and riddles, hinting that even in its infancy, the cosmos played by rules we're only beginning to glimpse. What if the Big Bang wasn't the beginning, just the latest chapter in an endless cosmic cycle? The idea of a cyclic universe where expansion and contraction repeat in an eternal loop isn't just poetic speculation. Hidden within the cosmic microwave background's faintest anomalies might be clues that our universe was born from the ashes of another, destined to collapse and rebound again. The theory offers a radical alternative to inflation, suggesting that instead of a singular, explosive birth, space-time has been pulsing like a heartbeat for eternity. But does the CMB's data whisper hints of this rhythm, or does it silence the idea for good? Cyclic cosmology hinges on a dramatic premise. Each universe ends in a big crunch, collapsing until quantum effects trigger a new expansion. Unlike inflation's clean slate, a bouncing universe would carry scars from its predecessor, subtle imprints in the CMB's temperature and polarization patterns. For instance, if previous cycles stretched and sheared spacetime, they might leave behind statistical oddities in the CMB's fluctuations, like faint concentric rings or residual gravitational waves with distinct spectral signatures. It's like finding fossilized ripples in a pond, evidence of stones thrown long before you arrived. The challenge: these signals would be achingly subtle. While inflation predicts near-perfect Gaussian randomness in the CMB, cyclic models allow for non-Gaussian memory from prior cycles, subtle correlations between temperature fluctuations that defy standard randomness. Some researchers argue that certain large-scale anomalies, like the infamous cold spot or the hemispherical power asymmetry, align eerily well with collisions between our universe and a neighboring one in the cyclic framework. Imagine two soap bubbles grazing each other during a bounce. Their interaction could leave a bruise in the CMB's fabric, yet the cyclic model faces brutal mathematical hurdles. To avoid a chaotic collapse that would erase all structure, each bounce must preserve just enough order to seed the next universe's galaxies, a fine-tuning problem rivaling inflation's own. Critics also point to entropy. If each cycle adds disorder, why hasn't the universe descended into thermodynamic chaos after countless iterations? Proponents counter that entropy might reset during the bounce, a notion that stretches current physics to its breaking point. The CMB remains the ultimate arbiter. If future polarization data reveals primordial gravitational waves with a spectrum only a bounce could produce, or if anomalies like the axis of evil prove too pronounced for inflation to explain, the cyclic universe might claw its way from fringe to forefront. Until then, it stands as a tantalizing what-if, a reminder that the universe's first light might hold echoes not just of its birth, but of its many deaths. The cosmic microwave background might be more than just an ancient light. It could be a cosmic projector screen, flickering with the holographic echoes of a deeper reality. The holographic principle, a radical idea born from black hole physics, suggests our three-dimensional universe is actually a two-dimensional shadow, a projection of information encoded on some distant, unimaginable surface. If true, the CMB's temperature fluctuations wouldn't just be random noise. They'd be pixels in the universe's ultimate display, each one a fragment of a code we're only beginning to crack. At its core, this idea springs from a startling realization. Black holes trap information in their event horizons, compressing everything that falls inside into a two-dimensional imprint. Extend this logic to the entire cosmos, and you get the holographic principle, a universe where the true action happens at the boundaries, with our 3D reality as an emergent illusion. The CMB offers a way to test this. If the universe is a hologram, its information content should be finite, constrained by the surface area of the cosmic horizon, not its volume. This would leave subtle statistical fingerprints in the CMB's fluctuations, like a painter's brushstrokes betraying the limits of their canvas. Some researchers argue these fingerprints are already visible. Analyses of the CMB's power spectrum reveal a curious suppression of fluctuations at the smallest scales, as if the universe has a pixel size, a fundamental graininess that can't be smoothed away. It's like zooming in on a digital photo until it dissolves into blocky squares. The CMB might be doing the same, revealing the underlying grid of reality. Other studies focus on entropy. The holographic principle predicts a strict upper limit on how much information any region of space can contain, which translates to a maximum entropy density. When cosmologists calculate the entropy implied by the CMB's structure, it aligns suspiciously well with these holographic bounds, as if the early universe was operating at the edge of its data storage capacity. But skeptics aren't convinced. The CMB's statistical quirks could stem from mundane sources, instrumental noise, foreground dust, or even the aftereffects of cosmic inflation. Without a unique holographic signature that can't be faked, the principle remains tantalizing but unproven. Some theorists propose wilder tests. If the universe is a hologram, quantum entanglement between distant CMB photons might follow non-local patterns impossible in classical 3D space. Future polarization experiments could hunt for these ghosts of a hidden dimension. Though the technical challenges are staggering, the implications are dizzying. If holography is real, the CMB isn't just a relic. It's a Rosetta Stone for decoding the universe's true language. Every temperature fluctuation, every polarization swirl, could be a symbol in a cosmic alphabet written on the edge of reality. Whether this idea survives future tests or fades into the annals of bold but unverified theories, it forces us to confront a humbling possibility. The universe's oldest light might be showing us not just where we came from, but what we are, a shadow play cast by forces we've yet to imagine. What if the cosmic microwave background isn't a relic of the Big Bang, but a rendering error in the universe's source code? The simulation hypothesis, a fringe but persistent idea, suggests our reality might be an artificial construct, an ultra-advanced civilization's digital project. And the CMB's anomalies, glitches in the system, artifacts of imperfect coding or computational shortcuts in the simulation's physics engine. It's a wild claim, but one that forces us to ask, if we were living in a simulation, what traces would it leave in the oldest light we can see? Start with the cold spot. This bizarre, supercooled region of the CMB spans nearly 2 billion light-years, a cosmic blank space where the temperature dips inexplicably. Simulation theorists argue it could be a texture mismatch, like a video game failing to load high-resolution terrain, leaving behind a low-detail patch. In their framework, the cold spot might be where the simulation's algorithms strain to cover vast distances, compromising accuracy for efficiency. Or consider the axis of evil, that eerie alignment of SIMB fluctuations along a preferred plane. Could it be a coordinate artifact, a relic of the simulation's underlying grid system, like the pixelation you'd see if you zoomed too far into a digital image? Even the CMB's near-perfect uniformity raises questions. Inflation explains it as a rapid smoothing of quantum noise, but simulation proponents offer an alternative. The early universe was pre-rendered by the simulators to save processing power. Think of it like a game developer baking lighting into a static environment rather than calculating it in real time, an efficiency hack that leaves telltale statistical signatures. The CMB's Gaussian randomness, they argue, might be too perfect, lacking the subtle correlations natural chaos should produce, but critics shred these arguments with Occam's razor. Every anomaly simulationist site has a plausible astrophysical explanation, from cosmic voids to instrumental noise. The cold spot could be a remnant of a supervoid or a statistical fluke. The axis of evil might stem from overlooked galactic dust. More damningly, the simulation hypothesis is unfalsifiable by design. Any evidence against it can be dismissed as part of the simulation's elaborate design. It's the ultimate cosmic conspiracy theory, immune to disproof. Then there's the energy problem. Simulating a universe atom by atom would require incomprehensible computational resources, far beyond any plausible technology, even for a super civilization. Some theorists counter that the simulation might cheat, calculating only what observers perceive, a just-in-time rendering. But this raises another paradox. Why would simulators waste cycles generating a CMB at all? Its existence only makes sense if the simulation's goal is to mimic a self-consistent, physics-driven universe, which circles back to needing near-infinite computing power. Philosophically, the debate hinges on probability. Proponents argue that if advanced civilizations routinely run ancestor simulations, the odds favor us being in one. But this ignores selection bias. We can't know how common such simulations would be, or whether they're even possible. Meanwhile, the CMB's precision measurements align exquisitely with standard cosmology, a web of interdependent predictions that would require flawless coding to fake. It's like finding a perfectly forged painting where every brushstroke matches the artist's biography, down to the pigments available in their era. The simulation hypothesis ultimately reflects a deeper tension, our hunger for meaning in cosmic patterns. When faced with anomalies, it's tempting to anthropomorphize them, to see a programmer's hand where there might just be chaos. But the CMB's greatest gift is its challenge to stay curious without surrendering to easy answers. Whether glitches or natural wonders, its mysteries remind us that reality, simulated or not, is stranger than we've imagined and far more wondrous. From the eerie alignment of the axis of evil to the unsettling void of the cold spot, from the phantom pull of dark flow to the whispers of decaying dark matter, each of these 30 mysteries woven into the cosmic microwave background isn't just a puzzle to solve. They're invitations to rethink reality itself. Every anomaly chips away at the edges of our understanding, revealing how much we still don't know about the universe's birth, its structure, and even its ultimate fate. The CMB isn't just a snapshot of the past, it's a mirror reflecting the limits of our knowledge, showing us where the cracks in our theories begin. Take the Hubble tension. A disagreement over how fast the universe is expanding might seem like a technical quibble, but it's a seismic rift in cosmology. Could it mean dark energy isn't constant, that gravity behaves differently on cosmic scales, or is there an entirely new force at play? Then there's the haunting absence of superclusters, the ghostly hints of primordial black holes, the spectral whispers of varying physical constants, each one a doorway to a universe far stranger than we've dared to imagine. Even the CMB's near-perfect uniformity, long hailed as evidence for inflation, might be hiding deeper truths about cycles of cosmic death and rebirth, or even the holographic nature of reality itself. But here's the thrilling part. We're not stuck in the dark. The next generation of experiments, CMB S4 with its razor-sharp polarization maps, the James Webb Telescope peering into the universe's first galaxies, next-generation gravitational wave detectors are poised to turn these mysteries into breakthroughs. Imagine uncovering definitive proof of cosmic strings, catching a multiverse collision in the data, or finally nailing down dark matter's identity. The answers are out there, etched into the ancient light we've only begun to decode. So what's next? It's not just about waiting for new data. It's about staying curious, questioning assumptions, and embracing the chaos of discovery. The CMB has already rewritten cosmology once. It's ready to do it again. And that's where you come in. Which of these mysteries keeps you up at night? Is it the chilling enigma of the cold spot, the cosmic audacity of a simulated universe, or something entirely unexpected? Drop your thoughts below, because the next big revelation might start with a conversation. After all, the universe's greatest secrets aren't just for scientists. They belong to anyone daring enough to look up and wonder.